Professor Devashish Sarkar, Department of Applied Mathematics, University of Calcutta. My topic is Quantum Information and Computation, an introduction. Since there is a talk on quantum computation, for that reason I will restrict my lecture today on quantum information theory basically. This is a very much important subject in these days, and I will try to explain my slides through my slides as far as simple as possible, so that you can learn this subject a little bit and take your own interest to the next few days and in future. My first main slide is that this is a subject where I need some background things. So, for that reason I will start with some background things. The early age of modern science has two fundamental subjects developed in this last century. One is relativity theory, another one is quantum mechanics, and both have many things in we have seen in the last century ago's. Now, for the proper understanding of the subject, I want to mention a new subject, the quantum information of computation, just developed in the last 20 to 30 years ago, and I shall try to give my lecture in such a manner, so that people can, or the students can understand, or you can understand it is a in a very simple manner. The subject quantum mechanics is in the heart of this new subject, and a new term quantum correlation appears in this, in the development of this subject. Okay. Now, before going to express my lecture, I will shortly or briefly give the main things of the three subjects. One is quantum mechanics, another one is information theory, and third one is computer science. And obviously, the underlying logic is governed by highly sophisticated mathematics. So, for that reason mathematician, physicist, information theorist and computer science all can be interested in these lectures, and whatever may be the audience, I will try to make my lecture as simple as possible. I will go to the next slide. Status of the subject mentioned, quantum mechanics. This is the most advanced and developed branch of modern science. Its achievement is enormous. The experimentalist is so much fascinating in this subject that theoretical predictions has a good and excellent agreement with the experimental facts. The governing laws of quantum mechanics is some axiomatic way, because there is no law like classical physics, like Hamilton's principle, D'Alembert's principle, like that in classical mechanics. Here we need some axiomatic way. The subject is very much interesting. It has many results which are counterintuitive in sense. Almost all the inventions of quantum mechanics in the initial days comes from the behavior of the particles in a very small dimension, like the theory of relativity, which developed where the situation is that the speed is enormous. From physical point of view, the subject quantum mechanics deals with the fundamental particles like proton, neutron, electron, photons and some other elementary particles which are needed to describe a new mechanics. Usually the behavior of that particles is not exactly the same what we deal in the classical frame, and for that reason we need a new subject quantum mechanics, and it has developed in the last century very well, like the theory of relativity also developed in the last century. My next subject is the information theory. It is a subject of communication theory. Its basic task or objective is to send or process information or data to distant location or labs through some channels, transmission channels actually reliably. This word is very much important. Reliable transmission is required for the proper processing of the informations. Practically reliable transmission is very hard. We need proper technology to transmit reliably informations. Therefore, the subject is challenging in both ways, theoretical as well as in the sense of experimentation and implementation. My next topic is the computer science. This is a subject generates lot of interest in the last 40 to 50 years. A high level computer has the ability to compute a result within a very few seconds or minutes, or sometimes it requires some more times, which is actually impossible for human beings to within a finite time to develop these things within a very short time. The basic ingredients of computer science is nothing but parallel processing. It gives the power of this subject, this parallel processing. So, you must understand these things. And another one thing in computer science is that its complexity, deals with its complexity, algorithmic complexity. There are two types of complexity, one is time complexity, another is space complexity. This an efficient algorithm requires these two things. Now, we go to the next slide, where I will try to describe my own lecture, today's lecture on quantum information and computation. What is quantum information theory? Its basic task is the same like information theory, to process informations, but using quantum mechanical principles. It is a fundamental things different from the classical information theory. You have to use quantum mechanics to process some information and data. For usual information theory, we require classical physics, where the mathematical theory is due to Kolmogorov and others. So, this branch is very much new. We need to describe in a little detailed way for proper understanding of this subject. I will explain my subject giving 4 examples, so that you understand that how this subject develops in the last 20 or 30 years. Why it is important, you also understand in my lecture. I give the 4 examples. One is BB84 protocols, next one is Dwyer-Joshua algorithm, third one is quantum teleportation, and fourth one is dense coding. I will try to explain first 3 elaborately, and fourth one just I will mention that things. What is the responsible factors, means quantum factors. First one is the non-orthogonal states, which actually means in the physical sense we cannot distinguish all. In classical physics, all things are distinguishable, but in quantum mechanics all are not distinguishable perfectly. Another responsible factor is quantum entanglement, a kind of quantum correlation. It is like energy in classical physics, in quantum information theory, but for quantum entanglement we need two or more parties or particles, and it is a new kind of behavior. We want to understand this properly. I will explain in the later slides these things as simple as possible. Now, I go to my first example, BB84 protocol. Its main area is cryptography, and this subject is very old, from the early age of Julius Caesar, and the things you know that Julius Caesar sends his information to his army by sending some cryptic language. So, the main objective is to distribute a key, secure key, from a sender to a receiver. One want to send some information with secretly. Now, third party, the eavesdropper, has always interest to know the information they are sending. It is very much important in everyday things like army and some other bank, etc. In many places, cryptography is a very fundamental things. Now, in classical cryptography, in principle, any protocol can be known by some eavesdropper. In principle, within a finite time, he or she will able to extract the information sent by sender to some receiver. It is in principle possible. But the new things in quantum cryptography is that within a finite time, if someone, that is eavesdropper, wants to learn the message, he or she will be caught it. This is qualitative difference from classical cryptography to quantum cryptography, and BB84 protocol is such a kind of protocol, gives in 1984, and incidentally our country is related in this invention. In the conference at Bangalore, Bennett actually gives this lecture. He is a profound scientist in this field. Now, I will explain protocol in short. Alice creates a random bit with 0 1 1, encoded its data either on Z basis or on X basis. You must know that Z and X basis are two different kind of Pauli operations. After receiving Bob also measures his qubit with Z or X basis, and after comparing their results, they will actually share a key. After that, they will give the public, and if some third party try to intervene in intermediate time, they will, by comparing their result, they will learn that some third party is trying to intervene in this process. Then they will just throw out their key and take another key. This is the things in this matter. So, it is a very important qualitative change is given in this important protocol by Bennett, Brashad and others. Now, my next thing is a quantum algorithm. It is given firstly by David Deutsch and later on Joshua. So, it is now known as Davis Deutsch-Joshua algorithm. It is a very simple matter. Anyone have some small understanding of mathematics will learn that. It is a matter that we have a task, that we have a function which is either balanced or constant. By balanced means the function is two valued and it has a string of length say n. By balanced means half of the time the function takes the value 0 and half of the time it takes the value 1, and by constant means it throughout the all argument it takes either 0 or 1. A constant function means what is I am giving it. So, the algorithm is such that if you try to learn from a classical computer what is nowadays is it by a search algorithm or some other algorithms, you find that the time complexity of these things is in the order of the string length, that is with n or something else. So, there is a time complexity, it requires some time, but the quantum algorithm is interesting in that sense, you do not require such kind of things. There is a black box where these quantum things will happen, and with a measurement you will learn. Suppose you have given some colors, that blue colors represents function balanced and red color represents function constant, then you will see a blue light is of blue light illuminate, then you will say that it is balanced. If red light is illuminate, then you will say it is a constant function. So, with some operation in a black box, this is a quantum operation where you need some quantum logic gates, and interesting thing is that these logic gates are reversible in nature. It is a very much important in the computation theory. You know the logic gates in usual sense are not reversible, but quantum logic gates are reversible, because the underlying mathematical operation is a unitary in nature. Now, I will go to the my next example, quantum teleportation. This is a wonderful invention. Actually, this invention generates these subjects, quantum information and then quantum computation. It is invented on the year 1993. For that reason, I am saying last 20 or 30 years ago these subjects develops. It is given by Bennett and other people. There are many physicists as well as mathematicians. They are giving this protocol. Bennett is one of the key person for this quantum teleportation. The basic objective is to send an unknown information in a distant locations, whether it is possible or not. Before that, I will explain another things. It is known as quantum cloning. Why? Because quantum cloning says that unknown information cannot be copied. Now, I will explain little bit about these things. For cloning in bioscience, you know the dolly, the things happens in medical science very early. Now, in the people are interested in physics whether cloning is possible or not. Think about a Xerox machine. What is its basic task? In a blank page, we have to imprint a book matter or any other documents to print in a blank page. Cloning or copying is like that. You have a information encoded in somewhere, you also want to, in a blank page, you want to imprint this. What is quantum cloning then? Like say, suppose you have a electron in a particular state, you want to prepare another electron in the same state. Then you say that that electron is a cloning electron of the first electron. So, the information encoded in a quantum particle, you want to copy it to another quantum particle, the same information, then it will be called cloning of the information in physical sense. Now, what is the problem? The problem is that if the information is unknown, then you cannot copy the information. No cloning theorem states that matter. You cannot copy unknown quantum information. If it is known, then you can copy the information. If it is unknown, then you cannot copy. Therefore, the people think whether it is possible to send unknown information to a distant location by some quantum devices. So, this is a challenging task. So, send information to distant location means you actually teleported the information to distant location. So, how teleportation works? There is a sender, there is a receiver, they are situated in two different labs that can be thousands miles or more than that. And in between them there must be a channel, it is a quantum channel. You need to process quantum mechanically everything. Now, some source is given some unknown information to the sender, then sender will do some joint operation. This operation is quantum, this requires some understanding of mathematics as well as physics, and after the whole operation the receiver also do some operation, and after the whole operation the receiver will understand that his particle is prepared in the unknown information what is given by the source to the sender. But the basic thing is that both the sender and receiver will not know what is the information is. Actually, there could be some agency. Some sender wants to send unknown information to some other person who situated in very distant location, and there are some agency who will do these things. So, the agency would not in principle learn the things. So, the achievement of this teleportation protocol is that it succeeds always. There is a kind of channel, quantum channel by which you can succeed, and Bennett and his collaborator in their paper in 1993, it is published in Physical Review Letters, they showed that it is possible. So, unknown information you can transmit in distant locations. So, in quantum cloning you have a no things, and in quantum teleportation you have some yes things. So, physics shows some very counterintuitive things in these things. There are some small things I have written, those who have interest to go details of this and go details of the references I have given. Next thing is dense coding. So, dense coding is just reverse of the quantum correlation. So, I have explained the 4 examples. There are some observations, that is entanglement is the basic things and non-orthogonal states, and you find there are some highly sophisticated mathematics involved in this subject. You have to go through the details of the papers and the literature for these things. There are some comments regarding the technological part, how to implement the things. Many people are working in the experimental situation, but what is the possible technology? Recently we found that some experimentalists, they think that another 20 or 30 years we can build a viable quantum computer. So, it is we are again entering a new technological era within 20 or 30 years. The basic thing in my lecture you find that quantum correlation is the key word. For that I have spent some slides. You will go to the slides, you will find that these things are very much interesting, and you will learn the going to the slides. I am giving the things that what is its understanding and why we need this type of correlations, whether it is quantifiable or not. There are many things I am explaining in my slides. The next slide, the most important entanglement I have given. Basically, this correlation I spend lot. Before that, I explained basic things of quantum systems. What do you mean by physical system? What do you mean by observable state? What is the postulates basics? What are the governing equations, etc. For the state, you need some density operators, which are linear operators on the Hilbert spaces. The structure need you as a mathematician, you need Hilbert space structure, and Density operator is nothing but Hermitian positive semi-definite operators with trace 1. These are the physical states. What is the composite systems? These are nothing but the tensor product of the Hilbert spaces. So, you have to understand this mathematics very well. There are two kind of states, separable and entangled. Which are separable? I have given the things in the slides. Now, for pure states, pure bipartite state, we have some interesting results. By Schmidt decompositions, you have some decompositions. Pure product states have Schmidt number 1 and pure entangled states are more than that. What do you mean by physical operation? It is given by Krauss. It is nothing but completely positive operator and it has some representation. I have explained in the my slides. There is a basic kind of operator which are called separable superoperators and a kind of operation which I actually need in dense coding and teleportation is LOCC, and there is a very important result whether all LOCC is separable superoperator or not, and it is affirmed that LOCCs and separable superoperator the set as far as set is all LOCCs are separable superoperator, but the reverse is not true. Now, the question is whether entanglement is quantified like a weight machine or something else like these things. It is quantifiable, it has some standard states. Bell states is the standard state by which we can compare like 1 kg 1 gram weight or the centimeter or foot in measuring. Pure bipartite state is to be measured like this. This is the entanglement of these things, and there are some difficulties in entanglement theory. Everything I have tried to explain in my slides, and there are some comments regarding these subjects, development of this subject I have explained in these 2 or 3 slides, and I will give some references which are some freely available in the internet. So, you can go through the internet and give this reference for your proper understanding. I think I try to explain today's lecture something which you can take interest, because this is a very challenging subject for different subject fields. Thank you all.